Hi team, now I'm going to talk about the Orbit-Stablizer theorem, and it's my favorite topic of this class because it unifies two of the most important topics in this class, that of Lagrange's theorem, which tells us how orders of subgroups relate to the order of the whole group, and group actions, which is another really important concept. So the Orbit-Stablizer theorem is basically a restatement of Lagrange's theorem in the context of group actions. So what we mean here is if we start with our group G and it's acting on a set X. If I fix some element in X and I look at the orbit of that element, recall that the orbit is all of the points in X that I get by taking the various elements of G and applying them to X. That's the orbit. If I look at the number of elements in that orbit, and I multiply it by the number of elements of the stabilizer of X, recall that the stabilizer of X is a subset of G that consists of the elements of G that leave X unchanged. This product is going to be the order of G. I'll note that this is a little bit surprising because the orbit of X is a subset of X, and the stabilizer of X is a subset of G. But with Lagrange's theorem in mind, it's somewhat less surprising because it turns out, and you'll prove this on your homework, that the stabilizer of X is a subgroup of G. Which means if we apply Lagrange's theorem to the stabilizer of X specifically, we have that G is equal to the index of the stabilizer of X in G times the order of the stabilizer of X. And so, if we can show that these two things have the same number of elements, if there's a bijection between the orbit of X and the index of the stabilizer of X in G, then we have proven the Orbit-Stablizer theorem using Lagrange's theorem. So to give you some intuition as to why this is true, I'll note that we can have G act on its subgroups. And I'll have G act on its subgroups by saying let H be a subgroup of G. The action will be defined by taking G dot H to just be GH. That is, for every element of H, I multiply it on the left by G. So then, what this action does is it takes subgroups and it sort of translates them around So if this is a subgroup, multiplying by G translates copies of H around the group G. And the orbit of H is all of the cosets of H. So all of the cosets of the stabilizer, if I let the stabilizer be H, are exactly this index here. But if I think of G acting on its subgroups, the orbit of the stabilizer is exactly going to be this. There's more to prove, and it's outlined on your homework, but I wanted to give this intuition as to why these two theorems essentially say the same thing. Okay, and I'd like to do an example of how we can use the Orbit-Stablizer theorem to compute the order of the group. for instance, if we don't know it. So I will do an example where we already know the order, which is the symmetries of the cube. However, we could apply this to symmetries of any of our favorite objects, and the same method would work. Okay, so our goal here will be to study the symmetries of the cube by looking at how the symmetries of the cube act on either the faces, the edges, or the vertices. And we'll use that to compute the order of the group of symmetries of the cube in 3 different ways and show that they're all the same. Okay, so to do this, we need to know that the cube has 8 vertices, it has 12 edges, and it has 6 faces. Okay, so I have a cube right here, and I can count that if I'd like. I have 4 vertices on the top and 4 vertices on the bottom. If you've ever used a 6-sided dice, which is a cube, you know that there are 6 sides or faces of the cube. And then for edges, we can count edges where I see 4 in back, you see 4 in the front, and then there are 2 on the top connecting the back to the front, and 2 on the bottom connecting the back to the front, and those are my 12. Okay, so now we want to look at the action of the symmetries of the cube on, let's start with the faces of the cube, because we've already done this. We did this on our Groups 2 adventure sheet, I believe. So here, what does the orbit of a face mean? Well, it means all of the places to which the symmetries of the cube can take that face. But I can take this front face to any position that I want, right? I can take it to the top by doing this. I can take it to the bottom by doing this. I can take it to either side by rotating by 90 degrees, or by rotating by 180 degrees, I can flip it to the back. So I can take any face to any of the other faces. So there are 6 elements of the orbit of this action. And there's a word for this, by the way, if I can take any face to any other face, if I'm looking at the action on the faces of the cube, and every face can be taken to another, that's said to be transitive. So the symmetry group of the cube acts transitively on the faces of the cube. Okay, and then the next question is, how many elements are in the stabilizer? So let's look at all the elements that fix this front face. Well, I need to fix this face, which means I'm essentially going to need to fix any axis that goes through this face. There's only 4 things I can do. I can rotate by 90, I can rotate by 180, I can rotate by 270, or I could do nothing. So these are my only elements of the stabilizer. And if I multiply the number of elements of the orbit by the number of elements of the stabilizer, I get 24. And we saw this previously, that the symmetry group of the cube consisted of 24 elements. In fact, we computed it exactly this way, by using the Orbit-Stablizer theorem secretly. Okay, let's try this with edges, because this will be a new computation that we haven't done before. So let's look at the orbit of any edge, and I'm going to look at the orbit of this edge here. Okay, so I can take this edge to the other edge in the front by just rotating like that. I can take this edge to either of the edges in the back by rotating by 90 or 180 degrees. I could also take it to the top by rotating backwards by towards me by 90 degrees. By 180 degrees takes it to the back. By 270 degrees takes it to the bottom. But I could also rotate 90 degrees that way, and then rotate it towards me. And so I take this edge to here, or here, And so I can take any edge to any other edge, is essentially what I'm trying to say. So again, the symmetry group of the cube acts transitively on the edges of the cube. So the orbit then has 12 elements. So then I need to look at the stabilizer of an edge. So maybe I have a different face in front, but I'm going to look at this same edge, the ways of fixing this same edge. And when we thought through the various symmetries of the cube, in order to fix this edge, I essentially need to fix anything that goes through it. So in particular, I need to fix the axis connecting this edge to the opposite edge. I'm allowed to rotate by 180 degrees through that axis, but I cannot change that axis. So this means that there's only two elements in the stabilizer of this edge, and those are the one that does nothing and the one that rotates by 180 degrees. And I know that this answer is correct because when I multiply 12 times 2, I get 24, which agrees with my previous answer. Now, it could be the case that I'm wrong on both accounts, but I'm using also the reasoning that in order to fix this edge, I can't change this axis. Okay, finally, let's look at the vertices. So I'm going to take this top vertex and look at all the places to which it can go. But maybe you believe me now. So I'm looking for the orbit of this vertex. Maybe you believe me that it will be all of the vertices, right? I could rotate like this, like this, like this to get all the vertices on the top. And then I could rotate by 90 degrees. Could rotate by 90 degrees towards you, or me, and then rotate 90 degrees that way, 90 degrees, 90 degrees, 90 degrees, and get all possible vertices. So also, the symmetry group of the cube acts transitively on the vertices of the cube. So then the question is, what's the stabilizer? Well, in order to stabilize this vertex, we have to stabilize any axis through this vertex. So in particular, we have to stabilize the axis through this vertex and the opposite vertex. But we're allowed to rotate around that vertex, and so we can rotate, and the rotation through that axis is order 3. We observed this when we were looking at the symmetries of the cube originally. And Ava and I have a video where we compute the symmetries of the cube explicitly, and these are 3 of them. Okay, so I have 3, do nothing, rotate by 120, rotate by 240, and then I get back to doing nothing. These are my 3 symmetries of the cube that fix this vertex. But anything else that I do to the cube is going to, including this one, which is always the one I forget, is going to move that vertex. So there's 3 here, and again, this gives me 24. So I've computed the order of G 3 different ways, all of them agree. So a piece that I'd like to now discuss is I only looked at what happened to one face, or one edge, or one vertex. Why is that enough? So answer number 1 is that the Orbit-Stablizer theorem will hold for any x in X. However, for any element of the set, the numbers could be different. It turns out here that the numbers, if I had looked at this vertex instead of this vertex, that I would still get 8 and 3 as my orbit and stabilizer, but this is exactly because my symmetry group of the cube acts transitively on the vertices. If it did not act transitively, say if this vertex could only go to half of the other vertices, then I would have to consider the action of G on each orbit. And when I did that, I would still get that the orbit times the stabilizer is equal to the order of the group, but I could get different numbers for different orbits, for elements of different orbits. So I could have like 3 elements in one orbit and 4 elements in another orbit, and if I had 3 elements in the orbit, the stabilizer would have 8 elements. If I had 4 elements, the stabilizer would have 6 elements. I would have to compute those separately. However, in this case, and actually for any Pythagorean solid, the symmetry group happens to act transitively on each of the faces, edges, and vertices of that solid. Okay, so I wanted to work through this example just to see the orbit stabilizer group in action. Thanks, team.